So we're working on worksheet 14 today, and these are applications of logarithms, okay? These are the notes that go with worksheet 15. The first one is what's called Newton's law of cooling. It says an object that has been heated will cool to the temperature of the medium in which it is placed, for example, the surrounding air or water. The temperature of the object can be modeled by this. Now, for some reason, this is a great reflection of this. Looks exactly like this, okay? A little bit different. They use M instead of A here. But for some reason, on your reference sheet, it looks more like this. I apologize. I should have made it look like this. The only difference is on this one, you would add something over the other side, but actually we're going to end up subtracting. This one's easier. Okay, let me make that just as confusing as I possibly can. All right, I'm sorry. The idea here is that an object will cool exponentially, okay, to the temperature of its surroundings. So for example, if we take a cake out of the oven and we set it on the counter, it cools to room temperature eventually, right? It doesn't get colder than room temperature, it's to room temperature. Now, this Newton's law of cooling does ignore any changes to the surroundings. For example, if you take an egg out of boiling water and you put it in a mug with ice water in it, it will cool, but the ice water would also heat up, yes? A little bit? Okay. That's kind of ignored. In other words, when you take the pizza out, the fact that you might heat the kitchen up a tiny bit with that pizza sitting on the counter is kind of ignored by this. All right. Both of these formulas assume the surrounding medium essentially remains the same. An example of Newton's law, the curve, is shown at the right. Okay, the cooling constant K will have to be found for each substance first. And then we're going to find whatever they want the second time around. So we have to do this twice. We have to solve this twice. So the first example, everybody with me here? A cup of coffee has cooled from 92 degrees Celsius to 50 degrees Celsius after 12 minutes in a room at 22 degrees Celsius. How long will it take to cool to 30? Okay, we can't answer that question yet. We're ignoring that question so far. What we need to figure out is the cooling constant K. It went from 92 to 50. So this was its original temperature, and this was its final temperature for the moment, from 92 to 50. After 12 minutes, that would be time. In a room at 22 degrees, this would be the temperature of the surroundings or the medium that it's found in. Now, let me look. On Delta Math, they call it T sub A for the surroundings. I don't know where they get A. On your sheet, it says T sub M for the temperature of the medium in which it is placed, okay? Neither one uses T sub S for surroundings. All right, so this one right here uses S. All right, we're going to fill in these into the formula. So the final temperature minus the surroundings, the final temperature minus the surroundings equals the original temperature minus the surroundings. E to the negative K T, which is 12. All right. No matter how you start this, you will have to subtract. This is a better formula, the one we are using, than delta math, because if you used this delta math formula right here, sorry, I gotta find it. The first thing you're gonna have to do is subtract that t sub a over to that side. So I like ours better, okay, than theirs, in that, for that matter, okay. Oh, I wrote it on a different page, didn't I? Okay, let me write it on this page. So it was 50 minus 22 equals 92 minus 22 e to the negative k times 12. Is that what I had, guys? Okay, so let's do the easy parts. What's 50 minus 22? Okay, 92 minus 22 is e to the negative. Now, can I write that as 12k? Would that be okay with you guys? It says k times 12, so I'm going to write it as 12k. All right, where is our unknown? Where's what we're trying to find? In the exponent? So what do we have to do when it's in the exponent? We're going to have to take the log of both sides. But what does your Algebra 1 brain remind you we have to do first? Yeah, we do need to divide by 70. Now, sometimes that doesn't come out nice. Do you remember last week I did a lot of, let's just leave it until we have to type it in the calculator? I'm going to do that here. I'm going to leave it 28 over 70, even though it comes out a nice decimal this time. Okay. So I have 28 over 70 equals e to the negative 12k. My unknown is in the exponent, so I need to take the log of both sides. What kind of log do I want to use because it's base e? So I'm going to do ln. So over here we bring the negative 12k down in front times the natural log of e equals the natural log of 28 over 70, and we're going to want to type that in a second. But what is the natural log of e? It's just 1. So 1 times anything is just itself. So we just have negative 12k equals this. So what's the last step in finding k? What is the only thing I have left to get k by itself? Divide by negative 12. So be careful. The 28 over 70 is all in one parenthesis, and we have to close that before we divide by negative 12. Now we're going to get a real funky decimal. I got 0.0764 if I round to 4 places. I think, let me look at the delta math. That's what I usually do, is 4 for the k value. Okay, I already forgot what I said. 0.0764? Is that right? Okay, thank you. The delta math slide. I didn't put it on here till later. The delta math slide says, using this information, find the value of k to the nearest thousandth. That would be 3 places, right? Tens, hundredths, thousandths, okay? And then it says, when you're all done, round to the nearest degree. Okay, so they do it a little bit differently. So if we wanted to do 3 places, we could just do 0.076. I don't care. We can do it that way today. The key will have 4 places probably. All right. Now we're supposed to find the time for it to continue cooling down to 30 degrees. We're doing the second part now. How long will it take to get to 30 degrees? we're going to go from the original time, okay? We're going to go from the original time that it came out. So it was 92 down to, we want it to get to 30 now. So this is our original temperature, and our final temperature is now going to be 30. We're trying to find what now? Time. So we don't use the 12 minutes anymore. And the room is still 22 degrees, so this is our surroundings or medium or whatever you want to use for that one. Okay, so the final temperature we want it to get to is 30 now. The room is still 22. And over here, we still went from 92 in a room that was 22. All we're changing is the 50 to 30, except we're also going to be finding T. So what are we going to put in for up here for where it said, in the formula it said negative KT? Our negative K is 0.076, and we're looking for T. All right. The Delta Math questions are easier than these, but we're going to practice both. All right. 30 minus 22 is 8. 92 minus 22 is still 70. Over here we have e to the negative 0.076t. Process is exactly the same. What are we going to do? Going to divide and then take the natural log, and that's going to move the exponent out front. And so the last thing we're going to do is divide by, ln of e is just 1, so we're going to divide by negative 0.076. So we have the natural log of 8 over 70 divided by negative, make sure you put in the negative 0.076. And I got 28.5. Anybody else? I believe it said in Delta Math to the nearest minute. So I'll round that way on the worksheet today just to help you practice for that, okay? So let me scroll back up here. All right, so what we did, one more time, is we used an initial data point, the fact that it went from 92 down to 50 in 12 minutes, to figure out how long it would take in total for it to get down to 30. Now, the algebra is really not that tricky, right? After we did the little subtracting, we just divided and took the log of both sides. All right, spent a lot of time on that first one. Let's see if we can do this one more quickly. Example 2, same kind of question. It's in Fahrenheit, not Celsius, so temperatures we're a little more comfortable with. A cake is removed from an oven. The oven was 350. What is that temperature? When you take something out that's been in a 350 degree oven for a long time, what is the temperature of what you're taking out? 350, yes. This is the temperature original. The object was 350. It cools to 120. Okay, that's the final temperature momentarily. After 20 minutes, that's T. In a room that is 65 degrees, this is the surroundings, so we can use T sub S, T sub M, they call it T sub A. least S and M make a little bit of sense for me. S is surroundings, M is medium, which is the same thing, the room temperature. All right. How long will it take the cake to cool to 90? This, remember, is a separate question. We got to find K first. All right, so somebody start me out. Final temperature minus the surroundings would be 120 minus 65, good job, equals original minus the surroundings, which would be 350 minus 65, nicely done, e to the negative, and we're looking for K right now, and the time we have to work with is 20 minutes. All right, 120 minus 65 is 55 maybe? Somebody check me. 350 minus 65 is 285. E to the, and I'm going to write that as 20K, okay? I'm going to switch that negative 20K up there, just because we usually put a coefficient before the constant, or the variable. All right, what are the steps? Yes. Okay. Yep. So the first thing we're going to do is divide by 285. Whoops. And then we're going to take the log of both sides. We divided that 285 off. And can I bring this out front at the same time, guys, the negative 20K? Or is that too confusing? Everybody good? And what is ln of E? So all I have left to do is divide by negative 20. So I get K equals, and I'm hoping it's a little decimal because that's what it usually is. I already forgot. What was I typing, guys? 55 over 285? Was it negative 20? Thanks. 0.082? Because that delta math says 3 places, so that's what we'll go with. All right. Now we're going to do this one more time. What changes, though? Yes, the final temperature we want it to get to is going to be this 90. What was the original final temperature? 120. So we're just replacing the 120 right here with a 90. And we're replacing the K value, right? And we're trying to find T. All right, so 90 minus 65 equals 350 minus 65, which we already know is 285. E to the negative 0.082 T this time. So this is 25. Did I subtract right? This is still 285. We're going to divide by 285. And then we're going to take the natural log and move this out in front, which I didn't do a very good job of. Even enough room. Woof, that's all glued together. All right. Negative 0.082 T. Then I need to divide both sides by, oh, I forgot the ln over here. I'm going to divide both sides by negative 0.082. So that I just have t equals, natural log of 25 divided by, was it 285? Divided by negative 0.082. Whoops, that's not an 8. Round to 30 minutes. Okay. All right. Do you feel like you could work on Newton's law? We'll do one more at the end where we do it like, they just ask an easier question at the end in Delta Math. You don't have Delta Math homework tonight anyway, but I will show you the difference, okay? The next thing we need to talk about is half-life and double angle, double angle. Oh, I'm going to teach you trig in the middle of the lesson today, okay? No, half-life and doubling time questions. On your sheet, right here, does everybody see this one on your little half sheet? Okay. It says half-life and doubling. If you're talking about a half-life question, then R is a half. If you're talking about a doubling question, then R is 2. But it says down here, half H stands for the length of the half-life or the doubling time. And it's T over H up in the exponent. So it's R to the T over H. What that is, if you think about this, if I said the number of candy in the bucket is going to double every 6 hours. So in 24 hours, it's going to double how many times? 4. So the first thing you did was took 24 hours and divided by 6 to get 4 doublings, okay? So we have to divide by the length of the half-life or the doubling time. All right, so moving back, ooh, I've lost where I was. This says half-life function is the original value times 1/2 x over h. So the half-life of radium-226. Now, I got to tell you, this always confuses students. Radium-226 is the name of the element. That 226 has nothing to do with the problem, okay? But the half-life is 1600. That is the H. Suppose we have a 120 milligram sample. That is the original amount, which this uses P, I think, what does it use on yours? N sub 0 maybe? Okay. How much will remain? So we want the remaining amount after 4,000 years, that's T. So this is just a typing question. If we start with 120, and it is halving or 0.5, but it's doing it every 1,600 years, just like you said you would take 24 hours and divide it by 4 to get 6 halvings. Well, we're going to divide this up in the exponent. And we can literally just type that carefully. So it's 120 times 0.5 or just 0.5 or 1/2 to the power of 4,000 divided by, and I already forgot what it was, 1,600. Thank you. Okay, so 21.2. Everybody okay? Yes. Yeah, I don't know what Delta Math does for these kind of questions. I'm going to go with a 1/10, okay? 21.2 milligrams. If we have time at the end today, I can look up, because there are some eventually. Not till next week do I assign any delta math on this. How long until there will be only 10 milligrams remaining? So this time, we're starting with 120. It is having. The half-life is still 1600, but we want to know the time to get it down to, we could use X, they used X, sorry, you can use X, whatever. To get it down to what? 10, so the 10 goes over here. Now, this is where students make a little mistake. Sometimes they want to multiply these together. Can we do 120 times 0.05? No. We have to divide that 120 over to the other side. So we have 10 over 120 equals 0.5 to the t over 1600. Then as soon as we're looking for an unknown in the exponent, we do what? And it doesn't matter what kind of log, okay? Do you want me to do the other kind, or I'm going to keep using ln? Okay, ln's short and sweet, right? Now, as soon as we write ln or log of either kind, we can move that out front. Now, this time, we don't have ln of e, right? So we're going to be a little bit careful. So we have the log of 10 over 120 equals t over 1600 times the natural log of 0.5. Okay, what do you want to do next? You want to divide the log over there, okay? That's going to leave us t over 1600 equals, can somebody type that one in for me? Let's see. The natural log of 10 over, I already forgot what it was, guys. 10 over, and then divided by the natural log also of, oh yeah, half, okay. 3.585 or something, but then we have to do what? I would just leave that big long number in your calculator and then do the last step, which is, yeah, how do you get rid of divided by 1600? You're gonna multiply by 1600. About 5,736 years. 5736 if we go to the nearest year. All right, so watch for half-life or doubling formulas and use that formula on your sheet. Oh, here's a quick doubling one. The number of fruit flies doubles every 8 hours. How long until a single fruit fly produces a population of about 1,000? So what are we starting with? Our initial population of fruit flies is 1, apparently 1 pregnant fruit fly, right? And what is the rate we're going to use? So if you're looking at your sheet, it looks like this. Okay, so doubling is our rate, R equals 2. It is doubling every 8, H is 8 hours. How long? We're looking for T. And we want to end up with 1,000 fruit flies. So it's 1,000 equals 1 times what? 2 to the t over 8. All right, we can divide the 1 off. That didn't change anything. And then what? It really would be easier to use log this time, but it doesn't matter. We're going to use our calculator anyway. So if you want to do ln, we can. As soon as we divided the 1 off already, then we're going to move this out front. So we have t over 8 times the log of 2. Everybody okay? What do you want to do next? Log of 2 over there. All right, so that leaves us with a t over 8 equals 1,000 to, everybody get about 10? And then we have to do what? Multiply by 8? So about 80. What was it? 9.966 or something times 8. Rounds to about 80 hours. I don't think I've ever made an 8 in my life like that. I don't know what just happened. My brain was... Okay. All right. We have one more thing to learn today. Oh, just kidding. We're still doing... All right. A wooden artifact from an ancient tomb contains 65% of the carbon-14 that is present in living trees. How long ago was the artifact made? So they're giving us a percent, but it really is what did it start with and where did it end up with? So if it started at 100%, it's down to 65%, okay? So if it helps you, this is what they do. They say, well, I'm going to do it this way. I'm going to say there was 100 and it's down to, I'd rather, okay. 100%, yeah, 100% would be 1 as a decimal and 65% would be 0.65. So I'm going to use that the original was all of it, and we're down to 0.65. Okay, then what? What is our rate we're talking about in this problem? It's a half-life, okay? So our rate is 1/2 or 0.5. And carbon-14, again, the 14 is part of the name. The 5730 is how long it takes to half, that's H. So we have T over 5730 up here. Okay, if we divide by 1, does that change anything? Nope. So we can use some kind of log. And we can move that out front. Okay, what do you want to do next? And you can just use 0.5. I probably should have just written 0.5. I would just, it's a half-life question, so I was thinking of it as a half. So we have T over 5730 equals 0.65 divided by 1/2, 4.5. 0.6215, something like that. And what are we going to do with that? Yep, we're going to multiply both sides by 5730. Was it 30? 5730. Okay, suddenly I was questioning myself. About 3,561 years. Three, 5, 7. I already forgot what I said. Okay. All right. We need to talk about logistic growth still, so I'm hoping that's the next question. All right. Logistic growth is when something grows but flattens out. Okay. It has a maximum. It has a horizontal asymptote up here. This is not logarithmic growth because logarithms, remember, had the range was to infinity. Okay, and eventually it would keep going. Logistic growth really refers to something that has what's called a carrying capacity or a maximum. For example, a population, if we went out to Rock Cut and we introduced some new species, there would eventually be a maximum number of those animals that the environment would support. They would either become overpopulated and start dying off, or there would be a certain number that there wouldn't be enough food for them or something, okay? That's called the carrying capacity. So we introduce an initial population. It usually grows quickly, but it will eventually flatten out. All right, so the population of frogs after T years in a pond is modeled by this, okay? And then we're going to find the initial population of frogs by putting in times 0. When will there be 100 frogs? We're not going to try to work this backwards. We're just going to graph the line. Y sub 2 is 100. And what is the projected maximum number of frogs? That's the carrying capacity. Did anybody notice where that carrying capacity always is? If I go back here, the carrying capacity is the line. It is the number at the top, okay? As long as it's a number alone on the top and the denominator has a 1 plus, then it is just that number on top. And you could check it if you scrolled off to the right far enough. So we have 120 maximum frogs here in ours because that's the number on the top. All right, so go to your graphing calculator. So pick up and go to graph. Oh my goodness, I have a mess. Okay. Then we're going to type very carefully 120 divided by, and we need some extra parentheses around the whole bottom. And it was 1 plus 14, which we cannot combine because the 14 is multiplied by E. So I'm going to use second ln next to the 4 there, and it's going to put me up in the exponent. And you got to be really careful, guys. This is negative 0.6 t. We're going to use x. Negative 0.6 or negative 0.6 if you want to put the 0 out there. As long as you have a 0.6, you're good. And then an x up there. Now, I'm going to arrow to the right and put a big parenthesis to show that I'm closing the parenthesis, but it would understand that you meant parenthesis at the end. Now, we do need to set a window. If we did a zoom 6, it just goes off the top. We're talking about number of frogs and time here. So can time be negative? Nope. And I don't know how long it's going to take. I'm going to go out to 20. So I'm going to go 0 to 10 and 0 to 20 here. Now, I know where the top is. What is the maximum number of frogs? 120. So I'm going to put like 130 here for my Y max, just so I can see the top. And you could make the Y min 0, because you really can't have negative, but I'm just going to leave it. I'm lazy. Okay, how's it looking? All right, how do we find the initial number of frogs? Trace to what? 0. Enter. Or you could look in the table. What's the initial number of frogs we put out there? 8. Then how did I say it? They want to know when it was going to hit what? 100? So we're going to put in Y sub 2, 100. Does anybody remember how we do that then? We find the what? The intersection. Good job. So second trace intersection. And you should be able to just hit enter, 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 because as long as you don't have anything extra in there. I got about 7 years or months, whatever it was. Did someone get that? 7.1? It was years. Yes, thank you. So initial was 8 frogs. And will be 100 in about, was it 7 years, guys? Okay. I like those. I think they're easy. They're just graphing questions. Just make sure you graph carefully. If it doesn't have that shape, you have typed something wrong, okay?
What are these words? I hit second trace and I'm looking for intersection and
Oh, I got it. Somebody put your calculator in German. Give me 1 second.